Okay, so we'll continue today our lectures. Today we will introduce Ohm's law, uh, Kirchhoff's laws, and which are basically voltage, Kirchhoff's voltage law, and Kirchhoff's current law. All those laws you have seen before in Physics 1010. We are going to refresh your memories and reintroduce them here. We'll talk about the resistors, the type of resistors we will be dealing with, series, parallel. We'll talk about circuit topology. What are the nodes? What are the branches? What are the loops? So let's start first with the resistivity. Resistivity is a unique signature for every material. Every material has its own resistivity. The resistance is a function of the shape of that resistance that you are building. So, as I said, resistivity given by rho here is a unique signature for every material. Every material has its own resistivity. Now, based on the dimensions of this structure that you are making this resistor from, you can see that it's also a function of the length and the cross section. The unit for the resistance is ohms. So just to give you an idea about that, if we go to the same website that we talked about last lecture from Colorado University, you can find this interesting application that basically put the uh, the resistance with the resistivity and the dimensions of the structure to show you what is the effect. As you can see here, the relationship between the resistance rho, the resistance R, and the resistivity rho is proportional. So if you increase the resistivity, the resistance is going to increase. And we define the resistivity as how easy the current can flow through this material due to the material itself that you're building this resistance from. The length, if you increase the length, the resistance is going to increase. So it's proportional to the length, and it is inverse proportional to the cross section, because once you increase the cross section, you are allowing an easiness more of the flow through this material. So the current will be flowing easily when you increase the cross section, and you can see it in this application. Okay, now back to our lecture. So just to compare the resistivity between or among other materials that we have, you can see that the silver here has the lowest resistivity in ambient conditions. So silver has a resistivity of 1.64 10 to the power minus 8. If you compare this resistivity, for example, with the paper here, you can see that the paper has a resistivity of 10 to the power 10, which basically gives a ratio of almost 6 times 10 to the power 18. So there's a huge gap between this insulator that is called paper and this silver that is called conductor. In between, we have also the semiconductors that are used in building semiconductor devices. Now, Ohm's law is basically the law that defines the relationship between the voltage, the current, and the resistance. So as you can see here, the relationship is proportional between the voltage and the current for a fixed resistance. So if the here unit for the resistance is ohm, we have here the unit for the current being ampere, and the voltage is being volts. So something to keep in mind that for a passive component like a resistor, we have said that the current is always entering the positive terminal, leaving the negative terminal. So this is always the case for the resistor. We have special cases of the resistors. We have seen what's called the short and the open circuit. So in the case where I have, for example, a wire that has zero resistance connected here at this output, for example, between those two terminals, what's going to happen? In this case, I will be withdrawing the maximum current I can because the resistance here is zero. So if there is no protection circuit for my uh, power source that I am using, I will be ending damaging this power source because I will be withdrawing a maximum current, and this maximum current will result into a withdrawn power that is beyond the capability of this power supply, which is basically going to result into damaging this power supply unless you have a protection circuit in this power supply. So if I have a wire here, I would be getting a maximum current. And of course, as a result of Ohm's law, if you apply Ohm's law, V equals to R. If you have R as zero, you will get a voltage of zero. So whenever you have a wire that has a zero resistance, the voltage drop across this wire will be zero. Now, what's going to happen for the other case, in case you have an open circuit? In case you have an open circuit, and back to Ohm's law again, V equals to R. If you have an open circuit, this means you have zero flow of charges, which means I here would be zero, right? And in this case, if I is zero, then here for this resistance, you have an open circuit. Again, I is zero. And in this case, if you want to calculate now the resistance for this uh, circuit, it will be V divided by zero. And this means you have an R of infinity. And this resembles an open circuit. So whenever you have an open circuit, as we have seen earlier when we introduced the ideal current source, it's an ideal current source, which basically means an infinite resistor that is connected in parallel to that source. So whenever we have an open circuit, this open circuit basically means an R of infinity. Linearity for the resistors basically means that I have a constant resistance along the range of operation. My resistance is not changing along the range of operation, and this is expected for those resistors that they do have a constant resistance. However, once you push this resistor beyond safe the safe range of operation, the resistance is going to change and this may result into damaging the resistor. But in this case, you will be operating it beyond the maximum power of dissipation that those resistors can handle. But here in this course, our resistors are linear. The nonlinear behavior can be seen in other devices like diodes and light bulbs, where the resistance is basically changing, not being constant. And this is based on the material and the conditions that those light bulbs are manufactured to operate under. But for our case, those resistors are a linear resistors. Now, the power dissipation is nonlinear because, as you can see here, if I say that the power is the voltage times the current, and then I substitute the voltage with its equivalent or the current with its equivalent. So in this case here, I know that V equals to Ri. So if I substitute V with Ri, I get the power of dissipation to be I squared R. And as you can see here, this relationship is nonlinear. Or if I substitute I with V over R, in this case, I get a relationship for the power, however, in terms of the voltage and the resistance, but it is again nonlinear because the voltage here is squared. Now, notice in both cases, the resistance is constant. The resistance does not change. So this is very important to know because this is the value in your equation that is going to stay the same. The resistance is not going to change. Only the readings are going to change based on the amount of voltage that you are applying across this resistor is going to result into a corresponding current. So the resistor is not going to change. Only the readings for the voltage and the currents are going to change. And also keep in mind that the resistor is a passive component that does not generate power. Now let's look at the example we introduced in last lecture, but at that time there were no information given about those components. Here, so in this circuit here, we want to calculate the power supplied or absorbed by each element. Remember, in last lecture, we said that the convention is if the current is entering the positive terminal, then this component is, and the reading is, if the direction of the current that corresponds to this reading, if the power is positive, this means that this component is absorbing power or energy. If the power is negative, then this component is supplying power or energy. So in this case, if we have here the current entering this component that is the power given to as P2, so in this case, I have the voltage, I have the current, so P2 would be V times I, and P2 would be 5 times 12. And in this case, the P2 would be positive 60 watts, which means that the component number 2 here is absorbing power. What about P3? Also, I have the current in P3 entering. So in this case, 6 times 8, I have P3 equals to 48 watts, right? Now this current 5 ampere is the same current that is entering into the negative terminal of this voltage source. Then this P1 becomes minus 5 times 20. P1 is minus 100 watts. Now, this is the, if you recall, the current controlled current source, right? This is the current controlled current source. So the current in this case, we can calculate the current. It is 0.2 of that current I. So let me call this one I2. So I have I2 here as 0.2 times 5. I2 is 1 ampere, right? Now, notice that the voltage here, notice that this current source is in parallel with P3. What does this mean? This means that the same voltage drop across P3 is also across this current source. So here I have also 8 volt, and as you can see, this current I2 is entering into the negative terminal. So I have here P4 to be minus, the current is 1 ampere times the voltage is 8. So P4 is minus 8 watts. Now, if you add the supplied with the absorbed, you should be getting a total power of 0. So here, calculate the power supplied or absorbed for each component. Now, if you add P1 plus P2 plus P3 plus P4, you will get, we have here P1 is minus 100, P2 is plus 60, P3 is plus 48, and P4 is minus 8. And as you can see, is here. So you'll always get the power supplied to be equal to the power absorbed in any circuit. And this is based on the conservation of energy. Any questions so far? Yes, go ahead. Okay, so here we have this component that is called P3. So let me go here. We have P3 connected and parallel with my current controlled current source. So this one is 0.2 I. We had I here to be 5 ampere, and we have P3 here to have a voltage drop of 8 volts. Now, since both of them are in parallel, as you can see here, the current source and the P3 component, they're in parallel, which means that they share the same voltage drop. So I have here 8 volts as well. And remember, the current is going in this direction. My I2 here, that is 1 ampere, is going in this direction, which means it is entering the negative, leaving the positive. And in this case, this one was the P4. So in this case, I have P4 here being negative, I2 times 8. So P4 is minus 1. We did calculate I2 to be 1 ampere times 8. So P4 is minus 8 watts. Okay, great. Any other questions? You. If the arrow is pointing down, then yes, it will be positive. Because at the end, I'm looking at the current entering. If the current is entering the positive terminal, then it will be positive. If the current is entering the negative terminal, it will be negative, right? So based on the sign of the potential difference and the direction of the current. Okay. Yes, but here you have to be careful. Here, the current and the P2, for example, they will always be positive. Now, for this case, we don't know what kind of component is this, but in resistors, if you have a resistor, you will always get a positive power because resistors will always absorb power, right? So that's a resistor. So for this resistor, if I have the current going in this direction, then you have to put plus minus this way. If I have the current going in the other direction, you have to put the plus minus this way. If you are assuming those things, if they're given to you in the problem, then you have to work out based on the directions and the values that are given to you in the circuit. But just to understand, resistors will always absorb energy. Resistors cannot supply energy or power. Does this make sense? Okay. Now the solution for what we have done is also included in this slide for you. Now let's go to this example. In this example, we will basically calculate the current I. We'll apply, it's an example for Ohm's law. We will calculate the current I when the switch is in position number 1. And we also need to calculate the current I when the switch moves to position number 2. Now, something that you always need to keep in mind, that whenever you have a switch, you need to redraw the circuit because the location of the switch defines the circuit. Any change in the circuit by moving a switch will basically change the whole circuit. So here for position number 1, so I can say redrawing the circuit, My circuit now is going to look like the following. My circuit is going to look like this. And this is my current. Let me call this one I1, because the current here in this circuit is going to be different than the current and the second circuit when I do the switching. So if I call this one I1, and my resistance here is 100 ohm, then I can calculate I1 using Ohm's law. I know that V equals to R Ri. So here I1 is V divided by R. So I1 is 40 divided by 100. And now in this case, this one is going to be 400. Either I say 0.4 ampere or 400 milliampere. So this is my current for position number 1. Now what happens when my switch moves to position number 2? I have my circuit looking now like this. I have the same voltage, right? Now my current I2 is going in this direction. So I2 now is based on Ohm's law, 40 divided by 250, and this one is I2 is 0.16 ampere or 160 milliampere. Any question? Now we need to introduce some of the circuits topologies that we have used and will be using. We have the nodes, we have the branches, and we have the loops that my circuit is made of. So as you recall, we said that the node is an electrical definition. It's not a physical definition here. All components that are connected together from one terminal are connected to the same node. So in this case, my node here, B, is a one distinguished electrical node. Why? Because as you can see here, all those components here are sharing the same wire. So this wire is going to generate a distinguished electrical potential, and that's why we called it a node. The same thing for C. If you color all the wires that are connected together, you can find this distinguished nodes. All wires that are connected together, they create a distinguished electrical node. And this is one of the most important uh, definitions and circuits that you have to be careful with, because this is one of the common mistakes that students are always doing when they define the nodes. And again, when we say a node, we refer to a node being an electrical in nature, which means it has a distinguished electric potential. And as you can see in the circuit, I have three nodes that each of them has a distinguished electrical potential. So this when it comes to the nodes. Now, what are the branches? The branches are those components that are between those nodes. So if I look here at my circuit, I can easily see that I have a branch here, a branch here, a branch here, branch here, and a branch here. Those are the branches that have the components confined within those nodes. So if I am to count the branches in this circuit, I can easily see that I have 5 branches. It corresponds to those components confined within those nodes. Right? Now the number of the loops can be basically calculated based on the number of the nodes and the number of the branches. And the equation is given by this equation. So we always said, if you recall, that the number of the loops equals the number of the branches minus n minus 1, where n is the node, b is the branch, and l is the loop. So those are the number of the independent loops that we do have and we need in our circuit in order to solve or do the analysis on that circuit. Okay. So here, if we look at this circuit, what do we have? We have B, we said as 5, minus, how many nodes do we have? We have 1, 2, 3 nodes. So 3 minus 1 is 2. So in this case, we have 3 independent loops that are useful in solving, as we will see later on when it comes to the KVL and the mesh analysis. Okay, so let's do this example. We have here this circuit. We need to calculate the number of nodes, number of branches and loops in this circuit. So if I take this to be as one node and this one to be my second node, then I have this one as my third node. So I have here n equals 3. Branches are 1, 2, 3, 4. So I have B as 4. And now if I put L equals 2, B minus n minus 1, then the number of loops would be 4 minus 2 equals 2. So I have 2 loops that are independent loops. Now, if you look at this circuit, you can easily see that you can make 3 loops out of this circuit. What are those 3 loops? This is one of them. I'll call this one L1. Whenever we define a loop, we give it a positive direction. So here we have L1, for example, as going clockwise. We have L2 as clockwise as well. And we can have this bigger one as also a loop. But based on this equation that we have used here, the useful loops that I can get are only two. So I need to pick two out of those three. This is just to give you an idea about the definition of the independent loop. Why? Because the third one can be derived from the first two. Whatever you do, if you take L1 and L2, if you add those together, you will get L3. So L3 is a redundant loop that is not useful to you. Any questions so far? Okay, so that's the solution to what we have done. Now, in my circuit topology as well, it is extremely important to understand the definition of the series and parallel, because those are sometimes seems to be uh, causing a lot of confusion to the students, understanding which is in series, which is in parallel. The definition is extremely simple, and you just need to understand that any two components that they share one terminal, and no other components are sharing that terminal, is going to result into a current, same current going into those two components. And in this case, we call those two components as in series. So if I have, let's say, this resistor that I am connecting here with this resistor. So this is R1, this is R2, and there are no other components that are sharing this node. Let me call this one node, because right now they have created a node, right? An electrical node. And there are no other components that are sharing this node. This is going to result into the same current going into those two components. And this means that R1 and R2 are in series. So they share the same current. The same current is going through both of them. So they are in series. If I have any component, any extra component, additional component that I added, for example, this is going to result into this current not being the same in both of R1 and R2. In this case, this current is going to split into I2 and I3. And in this case, R1 and R2 are definitely not in series. They're not in series. What do you mean? Doesn't matter. Doesn't matter. I'm looking here about, I'm looking at the case of R1 and R2. As long as there is someone who is share some other component that is sharing this node, this is going to result into a split into the current. So I1, this current in R1 is not the current going in R2. This means those are not in series. R1 and R2 is not in series. Even if there is a current, so it doesn't matter. If there is a current source, whatever, any other components that is going to affect the current going in R1 not being the same as the current going in R2, R1 and R2 are not in series. Anything. So in other words, there should be no other components sharing this electrical node to call those two components in series, right? So right now, they are in series, they are sharing the same current. Now the same thing here, it's a different feature for the parallel. The parallel, if they share both terminals, so if I have here R1 and R2, and both of them are sharing both terminals this way, this is going to result into the potential difference being the same across both of them. Now, regardless of whatever components I have here, R1 and R2 are connected in parallel. So notice that they are sharing both terminals, right? They're sharing both terminals, which means they have the same potential difference across both of them. This means that R1 and R2 are in parallel. I said it's up to me to define the positive direction. Yes, I picked it to be clockwise, and I said that this is the positive direction. You could have picked it the other way, counterclockwise, and assume that the counterclockwise is the positive direction for you. That shouldn't be a problem. Here we're talking about the loops, and we're going to come to the definitions and how to assign the loops. Here we're talking in general. We're talking in general. This is a circuit that has, as you can see, four branches, three nodes. The number of the loops are two loops, right? It doesn't matter the direction here of whatever you the clockwise or counterclockwise. It's not going to change anything. Okay, so Kirchhoff's laws. We have you have seen Kirchhoff's laws before in physics 1010. We will reintroduce Kirchhoff's laws here in this lecture, where Kirchhoff's laws basically we have one of them is voltage and the other one is a current, and they are based on the conservation of energy. So for the KCL or Kirchhoff's current law, the law says that the summation of the currents entering and leaving a node is always zero. So in this case, if I am to represent this summation here, I need to define the positive and negative for those currents based on entering or leaving. So if I am now to write the Kcl equation for this node, I need to adopt a convention about the direction of the current. So if I assume, and this is up to you, if you assume that the currents that are entering are positive, then the currents that are leaving should be negative. So if this one is entering and you wrote this one as a positive, then you have to write I5 in the equation as a negative. If you want to take the convention that leaving currents are positive, then you can write I5 as positive. But in this case, the currents that are entering the node have to be written as negative. So in this case, if I take one of the conventions, let's assume that the convention I'm taking is currents entering the node are positive. In this case, I will write I1 as positive. I will write I2 as negative, I3 as positive because it's entering, I4 again, I4 is entering as positive, I5 is leaving as negative. So this is how we write the KCl equation for any node. It creates a relationship between the currents that are sharing that same node. So if we look at this example, we need to determine V naught and I naught. In this case, I have here a current source, an independent current source, and I have a dependent current source that is current controlled. So if I am to calculate V naught, which is the potential difference across the resistor 4 ohm here, first of all, I can write KCl at the node A, taking the convention as, let's say, entering are positive. So I have here zero point 0.5 I naught as positive. I have I naught that is leaving as negative. I have 3 ampere it's entering as positive equals to 0. So look at the branches. It is very important. Look at how many branches how many wires you have here. Every wire is going to result into a current. As you can see here, I have 3 currents. One of them is this is the 3 ampere is coming this way. I have the 0.5 I node that's coming this way, and then I have I node that is going through the 4 ohm resistor. This is the KCl equation I could write, and as you can see, I have one equation, one unknown, then I can find 0.5 I node equals 2 plus 3 equals to 0, or I node is 3 divided by 0.5, I node is 6 ampere. So this is I naught. Then you can find V naught using Ohm's law. So I have here V naught equals to 4 times I naught. And as you can see here, the current is entering the positive. Very important to keep in mind. Resistors, the current is always entering the positive terminal. So in this case, I have V naught equals to 4 times 6, and V naught is 24 volts. So this example basically includes KCl and Ohm's law together as an example. If you don't have any question, we can move on to the next. Any question about how did we solve this example? Okay, so that's the solution also included for you here. The KVL, on the other hand, is addressing the potential difference in loops. So KCL was addressing the current behavior in a node. KVL will be addressing the voltage differences across a closed path, which is a loop. So what does KVL stand for? KVL, Kirchhoff's voltage law, is another conservation of energy law. It says that the algebraic sum of the voltage drops across a closed path should be 0. And this now comes to the usefulness of the direction of the loop, the one that one of your colleagues was asking about. So here, the summation basically means the following. Here, you have uh, the positive direction of the loop that you have adopted. For example, this is a clockwise. The positive direction is going clockwise, and in this case, if I have the positive direction of the loop entering the positive terminal here, as you can see, for example, I will write the voltage as a positive in my KVL equation. If I have the positive direction entering the negative, I'll write it as a negative. So for this loop, for example, if I apply this convention, this is the positive is clockwise, I can write V2 as positive. Let me expand this loop. If I'm to expand this loop, it's going to look like something like this, just to make it easier for me. This is the same as the red loop. However, I have expanded it just to uh, look bigger to you. So you can see that the loop is entering the positive terminal for V2, and that's why I wrote it as positive V2. Same thing, it's entering the positive terminal for V3. I wrote it as positive V3. It's entering the negative terminal of V4. I wrote it as minus V4. It's entering the positive terminal of V5. I wrote it as positive V5. And it's entering the negative terminal of V1. Then I wrote it as minus V1. So this is how we write the KVL equation for a loop. Any question about how did we write this KVL equation? No? Okay, so let's look at this example. In this example, we need to determine the V node and the current I. So V node is the voltage drop across the 6 ohm, and I is the current that's going in this loop. Now notice that all those components you're seeing, they have the same current and they all are in series. So this is something to keep in mind. All those components, they are in series. Okay, now we need to determine V naught and I. So let's, in this case, take this loop and write the KVL equation for that loop. So if I take my L1 to be clockwise, as you can see here, now I can write the KVL equation based on the convention that I have talked about earlier. So KVL at L1, in this case, what do I have? I have this L1 entering the negative terminal of the 12 volts, so I will write it as minus 12. I have now, based on this current that is entering the 4 ohm this way, I will say that this is plus, this is minus. And now this V equals to 4I, right? Based on the direction of the current that is entering the resistor of this way, this means it is entering the positive, leaving the negative, because this is the convention of Ohm's law on resistors. So in this case, I will write, if I say this one is V1, let's give it V1, then minus 12, entering the positive, so plus V1, entering the positive, plus 2 V naught, entering the negative, minus 4, entering the negative, minus V naught equals to 0. So this is the KVL equation I got out of my circuit. Right? Now, you can see here that this equation has two unknowns for me, V1 and V naught. Okay. Now notice that V naught is the voltage drop across this 6 ohm, right? So I know here, from here, I also know that since this current is entering this way, I can come up with a relationship between V naught and I. So I know that in this case, V naught equals to minus 6 times I, right? Notice that the current is entering in this terminal from this side, from the negative side. So V naught is minus I times 6, or minus 6 times I. This is the relationship that we found for the controlling parameter. So our controlling parameter here is the V naught, if you recall. So this is a voltage source, voltage source controlled by V naught. The relationship between V naught and I is this. We know that V1 also is 4I. So if I substitute V naught in here and V1 in here and also in here, I will end up with one equation, one unknown. So in this case, I have minus 12 plus 4I plus 2 minus 6I minus 4 equals 0. So rearranging, minus 4 minus 12 is minus 16. So I have here 4I minus 12I minus 8 plus 6I minus 2 minus 2I minus 16 equals to 0. And in this case, I have minus 2I equals to 16 and I equals to minus 8 ampere. So this is the current I, and then now I can substitute I in here to find V naught. So V naught is minus 6 times minus 8. V naught is 48 volts. So the current flows opposite to our assumption. Yes, that's correct. The direction of the current was given to me in this circuit, this way. It was assumed and dictated on me to be in this direction. However, when I worked out the problem, applied KVL and found the relationship between the current and my controlling parameter here, V naught, and solved it. Yes, you're right. I found out that the current is going in the opposite direction than it was assumed. Any other questions? So the current was going in the opposite direction. This clockwise thing is the direction of the KVL, is the direction of the positive KVL. Okay. This is the current. This is the positive direction of KVL. It's not, sometimes it's not that straightforward. You have to apply, you have to apply the laws first and do the analysis to make sure that you have the correct numbers. You cannot tell. Any other questions? So remember we talked about the series and the definition of the series resistors earlier in this course. And we have seen how two resistors that are in series, they have the same current. Uh, Now I want to take advantage of this to introduce what's called the voltage division. So remember, and resistors that are in series, and we have derived the proof that two resistors are in series are basically their equivalent resistance is the summation. You can easily prove this by taking here the KVL and adding those two voltages. So if you take the KVL, for example, here and take this direction to be this way, then you can say that this is minus V equals to V1 plus V2. However, minus V plus V1 equals to 0. However, this minus V is R equivalent I, and this V1 and V2, they are R1 I plus R2 I equals to 0. Then if you take this to the other side and take I outside, then this is R equivalent I equals to R1 plus R2. Take I outside, and then if you compare, you can know that R equivalent for the case of the resistance of the series case is the summation of those two resistors. So at the end, any resistors that are in series, the equivalent resistance would be the summation of those two resistors. Now, the voltage division rule here is basically finding the voltage, knowing the resistors. So, for example, in this circuit, I have R1 and R2 that are in series, and I know R1 and I know R2 and I know the total voltage, right? So you can call it a shortcut to calculate the V1 by the voltage division. And it says that V1 is proportional to the resistor that it is across divided by the total resistance that this source is seeing. So here V1 equals to R1 over R1 plus R2, which is the total resistance, times V. So R1 over R1 plus R2 defines the ratio. What is the ratio between the resistance that you're interested to find the voltage drop across to the total resistance? And you can derive this easily. If you go here and say that this is my voltage, this is my R1, this is my R2, where I have here V1 and V2. This is V and this is I. So again, back to the KVL thing. If you write the KVL, you are going to get V minus V plus V1 plus V2 equals to 0. Then if you want to find V1, then V1 would be V minus V2, right? However, you have to be careful here that the equivalent resistance here, our equivalent is R1 plus R2. So you need to write the relationship here. So what is I? You need to find I. I is V divided by R1 plus R2. Then you come here to V1 and you say V2 is indeed R2 times I, and then take this I, substitute it here. You end up with V1 equals to V minus I is R2 times V over R1 plus R2. And then if you take V outside, V1 would be V1 minus R2 over R1 plus R2. So V1 is V R1 plus R2 over R1 plus R2 minus R2. Then you basically, with the help of the voltage division, you're kind of saving, yourself all this time to do what I am doing right now. So I have here R2 would cancel, and you'll end up with the voltage division that we talked about being R1, the ratio between the resistor that I'm interested to find the voltage drop across, multiplied by the total voltage across the whole R equivalent. So this is the voltage division, and and how it's helping me in saving some time when it comes to calculating the voltages right away by knowing the resistances, which is basically end up to be the ratio of this resistance that I'm interested to find the voltage drop across to the total resistance that is making the equivalent resistance. Any question about that? Any question about the voltage division? So the same thing for V2. It's proportional to the resistance that I'm interested to calculate the voltage drop across to the total resistance that the voltage source here is seeing. You can expand this also definition on N resistors that are connected in series as well. Any question about the voltage division? Okay, so the parallel resistors, we've talked about them, and we have seen that resistors that are sharing both terminals and they have the same voltage drop across, they create resistors that are in parallel. So the current is not the same. The current is not the same. The current is basically based on the value of the resistance itself. So here in this case, you can see that this voltage source is across both resistors R1 and R2. So here I have plus V. This plus V is the same for both of them. Now the value of the current in R1 basically depends on the value of R1 itself, because V is the same, R1 and R2 are not necessarily the same, then definitely I1 and I2 are not going to be the same. So here you can say that the current is really decoupled. They have nothing to do with they don't influence each other unless you have a resistor that is sitting in here. Then this is something. Then in that case, it will be a bit different. But here, since the voltage is the same for both of them, the voltage is the same for both of them, then they are basically decoupled. So if you change this resistor, if you vary this resistor, this current is not going to change. I2 is not going to change. If you vary this resistor, only I1 is going to change. Why? Because now the voltage source here is across both of them, is going to supply the current for both of them based on their demands, which is based on the value of the resistance itself. Okay. Now, for resistors that are in parallel, if there are only two resistors, you can apply this expression here, which is the product divided by the summation. This is going to be the R equivalent for two resistors that are in parallel. So I would like to stop here. Our lecture is time is over. I would like to stop here, and then we will continue and next Tuesday. So I'll see you next Tuesday. If you have any question, please let me know before you leave. Other than that, please feel free to leave. Have a good weekend. Thank you. Thank you.